There's a special type of matrix that we're going to find particularly useful in solving systems of equations. And the, that type of matrix is a matrix that's in what's called row echelon form or reduced row echelon form. As we'll see, there's two different things here. So first of all, let's give a definition of row echelon form. A definition. You might recall I'm kind of keen on definitions in this class. So anyway, here's what row echelon form is. So a matrix is said to be in row echelon form if, one, well, there's the three things. So first of all, if a row does not consist entirely of zeros, then the leftmost non-zero number in that row is a 1. We call this a leading one. So this is like two definitions in one. We're defining what a leading one is, and partially defining what row echelon form is. This first condition, I might point out that the book words a little bit differently. Where I say the leftmost non-zero number, they say the first non-zero number. But the use of the word first means that you're looking at things from left to right. I don't know that everyone does that, so I think it's a little more precise to say leftmost. So it's not that the leftmost number in the row is a 1, but the leftmost non-zero number is a 1, right? So, I mean, looking at examples over here, you know, the leftmost number is a 0, but it's a 0. So the leftmost non-zero is a 1. Right? Each one of these matrices that I'm showing over here satisfies condition 1, right? Each row, if it's not all zeros, like this one right here is all zeros, but that doesn't matter, right? As long as it has something other than zeros, then the first thing, the leftmost non-zero thing, is a 1. Okay. 2, if there are any rows that consist entirely of zeros, then they are grouped at the bottom of the matrix. So this matrix here have one row of zeros each on the bottom. If you had more than one row, then you just have several non-zero rows. But you'll never have all zero rows. You'll never have an all zero row somewhere up here. Or if you do, then it's not in row echelon form. Okay. So anyway, any row that's an all zero is grouped towards the bottom. And 3, in any two consecutive rows that do not consist entirely of zeros, the leading one in the lower row occurs further to the right than the leading row in the leading one in the higher row. So notice, looking here, pick these two consecutive rows. The leading one is in the first column and the leading one is in the second column. So we're good. The lower row has the leading one further to the right. Any two non-zero rows that you pick, that would be the case. So this and this both satisfy number 3. This one, however, does not satisfy number 3 because here's consecutive rows, the third and the fourth row, where the leading one here in the lower row is actually to the left of the leading one in the higher row. So this is not row echelon form, where these two seem to be okay. Right? So I've got 2 of them in row echelon form and one that's not. Okay. Now we further say not only could we have row echelon form, but we might have a fourth condition, and if we satisfy this fourth condition, it is in reduced row echelon form. Row echelon form is going to be nice. Reduced row echelon form is even going to be better. And the fourth condition is each column that contains a leading one has zeros everywhere else in that column. So notice this one here. There's 3 leading ones. So I look at those 3 columns. There's zeros everywhere else in that column. This column here, the third column, has a 3 and a 4 in it, but it doesn't have a leading 1 in it, so I don't really care. This condition is only talking about columns that have leading 1s, right? This one up here, there's a leading 1 right there, but it doesn't have just zeros everywhere else. There's a 4 and a 5. So this is not reduced row echelon form. It was just row echelon form. This is actually reduced row echelon form because these zeros above. Right? Essentially, for row echelon form, you're looking for zeros down below and then leading 1s. Reduced row echelon form, you have zeros up above all the leading 1s as well. Okay? So that's the definition of row echelon form, and then reduced row echelon form. So those three things plus that one get you the reduced row echelon form. These are particularly nice because if you have an augmented matrix, if you're interpreting this matrix as an augmented matrix for a system, and it's a reduced row echelon form thing like this one, right? This has three leading ones. The columns, they're good. This last column doesn't have a leading one in it, so you don't really care what the values are. But this augmented matrix corresponds to this system right here, and it's particularly easy to solve this system. X1 equals 5, x2 equals 6, x3 equals 2. I mean, you're looking at the solution. So it's going to behoove us to be able to take a system, turn it into an augmented matrix, use some row operations to turn our augmented matrix into one that looks like this in row echelon or reduced row echelon form, and then have a system that's a lot easier to solve than the one that we started with. Okay, so the question is going to be, how do we create this? How do we do that? What's an algorithm for turning a system into an augmented matrix, and then that augmented matrix into a nice augmented matrix, and then getting a good answer out of that. And the method that we'll look at is called Gaussian elimination, or an enhanced version of it is called Gauss-Jordan elimination, and we will look at that in the next video.